The Global Positioning System, or GPS, is the United States version of a Global Navigation Satellite System, GNSS. The space-based navigation system can trace its roots back to the 70s when testing began. However, the system became fully operational back in 1995. The GPS system consists of three elements: space, control, and user. The space element consists of a minimum of 24 satellites in 6 orbital planes around the Earth. There are usually closer to 30 GPS satellites in orbit at any time. These satellites are in a medium Earth orbit at 10,900 nautical miles above the Earth. At this distance, they orbit the Earth every 12 hours, or twice a day, meaning they are not in geostationary orbit like communication and weather satellites. At this orbit, they travel roughly 7,000 miles per hour and at an inclination angle of 55 degrees from the equator. This is important because it allows 5 satellites to remain in view at all times from anywhere on Earth, except at the poles. Each satellite is built to last about 10 years, with replacements built and launched as needed to keep the system running smoothly. GPS satellites are powered by solar energy, but have backup batteries on board to keep them running during periods of solar eclipses. In addition, small rocket boosters are located on each satellite and are used to keep them flying in the correct orbit. Finally, each satellite contains 2 or 3 atomic clocks, which are the key components to getting your position. The control element consists of ground-based monitoring stations, a master control station, and ground antennas around the world. The goal of the control element is to ensure the accuracy of the GPS satellite positions and the accuracy of the atomic clocks on board. The master control station gets data from monitoring stations pertaining to errors with satellite orbits or clocks, and is able to send data and instructions to the satellites to correct for any errors detected or to move satellites back to their proper orbits. The user element consists of the combination of the antennas, receivers, and processors in the airplane that receives the signal and calculates your GPS position. There are a wide range of receivers, anywhere from handheld devices to panel-mounted to full flight deck systems, but they all perform the same calculations to give you your position, and each has their own limitations that the pilot must be aware of before using them for navigation purposes. Each GPS satellite transmits the GPS signal in the microwave range. The 2 primary signals are called the L1 and L2 frequencies. The L1 frequency transmits at 1,575.42 MHz and is for civilian use. The L2 frequency transmits on 1,227.60 MHz and is encrypted for use by the military, although these frequencies are not important to know. Each signal transmits a course acquisition code that contains 3 parts. First, a pseudo-random code, which is an ID code that identifies the transmitting satellite. This also prevents something called spoofing, which in simple terms prevents anyone from interfering with the GPS signal. Second is something called the ephemeris data, which is describing where each GPS satellite should be in orbit at any given time. And third is the almanac data, the current date and time, and the status of the satellite, whether healthy or unhealthy. The entire GPS signal takes approximately 30 seconds to receive. The idea of how the GPS works is based on a principle called pseudo-ranging. This is the name for the process that allows us to calculate our distance, not by actually measuring distance, but calculating it with a time calculation. This is done using the same formula from dead reckoning. Rate times time equals distance. Radio waves travel at the speed of light, which is 186,000 miles per second. The GPS satellite sends a signal to the airplane that has the time the signal was sent. The receiver can compare the time the signal was sent to the time the receiver received the signal. Since we know the speed of the signal and the time it took to get from the satellite to the receiver, we can calculate the distance from the satellite to the airplane. So the GPS signal that is sent out really is more like, I am satellite X, my position is Y, and this information was sent at time Z. There is one problem, though. This means that we are approximately 10,900 miles away from the satellite in all directions, essentially making a sphere that we are on. In order to pinpoint our location, we need to use more satellites. By adding a second satellite, there are now 2 spheres that intersect. This makes a circle of where we could be. A circle contains an infinite number of points, so we need to add a third satellite to get our position. By adding a third satellite, the sphere of our possible locations from the third satellite intersects the circle in two locations, one on Earth and one in space. By eliminating the location in space, we know our 2D location. In order to get a 3D location, a fourth satellite is necessary to remove any ambiguity in the position. The GPS satellite constellation is designed to make at least 5 satellites in view at all times, and most of the time there are several more received. If we receive more signals from satellites other than the 4 necessary to get our 3D position, the GPS receiver will use the additional signals in its position calculation and give the pilot an even more precise location. Now that we know our 3D position, we need to check the accuracy of the GPS signals. In order to do this, our GPS receiver calculates something called Receiver Autonomous Integrity Monitoring, or RAIM. This is the system the receiver uses to verify the usability of the received GPS signals, which warns the pilot of malfunctions in the navigation system. In order for the receiver to calculate RAIM, we need to receive at least 5 satellites. If RAIM is not available, the pilot will receive a message from the GPS to warn him or her that there may be some error in the GPS position. RAIM outages may occur when there are an insufficient number of GPS satellites, or there is an unsuitable satellite geometry, either of which can cause the error in the position to become too large. Just like every other navigational system, there are several GPS errors that a pilot can experience while flying. The first is any time there are fewer than 24 operational satellites, which may result in a lack of adequate GPS signal. Next, any time the antennas on the aircraft are blocked from receiving the signal by high terrain, such as in a valley. Or any time the aircraft's GPS antenna is shadowed by the aircraft structure, like when the aircraft is banked. Some other errors that can occur are harmonic interference from VHF transmitting devices, satellite atomic clock inaccuracies, receiver or processor errors, or even a bounced or multipath signal reflected from hard objects. There can also be errors caused by the signal traveling through the ionosphere and troposphere, which can cause a delay in the signal. Additionally, sometimes there are satellite data transmission errors, which may cause small position errors or momentary loss of the GPS signal. Finally, there was an error called selective availability. This is an error caused by the U.S. Department of Defense that can purposely cause error in GPS signals. This error was discontinued on May 1, 2000, but may be reinstated at any point in the future that the Department of Defense finds it necessary. So, to sum up, all of these errors, when added together, equal an error of plus or minus 15 meters, or roughly 45 feet. When selective availability was turned on, the error was plus or minus 100 meters, or about 300 feet. The less error we have, the better. To improve the accuracy, integrity, and availability of GPS signals, something called Wide Area Augmentation System, or WAAS, was designed. WAAS works so well that the location error is a mere 10 feet or so. As the GPS signal reaches Earth, it is received and monitored by ground-based wide area reference stations. These stations monitor the GPS signal and relay the data to a wide area master station. At the master station, a correction to the GPS signal is computed. A correction message is prepared and uplinked to one of the geostationary WAAS satellites via a ground uplink, and then broadcast on the same L1 frequency as the regular GPS signal. Any GPS receiver that is also WAAS capable will be able to receive the correction message. The receiver will then apply this correction into its GPS position calculation and display to pilots an even more accurate position. The WAAS satellites are in an ideal position for their geostationary orbit, allowing them to cover a large portion of the Earth. To take full advantage of their location, the WAAS satellites will also act as regular GPS satellites. In essence, there are always an additional 2 or 3 regular GPS signals available to pilots across the United States.